You know, what if I told you that one of the most common materials in the entire world, something you've probably been around every single day of your life, is just completely misunderstood? We're talking about gray cast iron. And yeah, it gets a bad rap. People think it's simple, old-fashioned, maybe a little brittle. But we're about to bust some of those myths. Just think about it for a second. That massive engine block in a car, it has to absorb incredible forces and vibrations, and it does that for hundreds of thousands of miles. Or what about the super heavy bases for industrial machines, the ones that have to be perfectly stable to work with absolute precision? These aren't just random material choices, folks. Nope, they are very deliberate engineering decisions, and they're all based on the unique properties of gray cast iron. So that's the real puzzle, isn't it? If this stuff is so old-fashioned and supposedly so brittle, why is it still the go-to, the absolute baseline material for so many critical components? I mean, why hasn't it been replaced by some fancy modern alloy? Well, the answer isn't on the surface. To find it, we have to go deep, deep inside its microstructure. Okay, so let's start with what most people think they know. Let's just get the common perception out on the table. When an engineer hears gray cast iron, their brain usually jumps to three things. One, it's cheap. Two, it's incredibly strong when you squeeze it. That's compression. But three, it's fundamentally brittle. You try to bend it or pull it, and snap. And its cost is for sure a huge part of the story. I mean, that's what makes it the default choice for these absolutely massive components. But cost alone, that doesn't explain its incredible staying power. To really get it, to understand its true value, we need to go a lot deeper. All right, let's do it. Let's put this material under the microscope and take a look under the hood. The real secret to both its so-called weakness and its hidden strengths all comes down to the unique way carbon decides to behave as the iron cools down and solidifies. And this is what we find. So on the left, you're seeing these flake-like structures of pure carbon that are just embedded in the iron. Now look over at the image on the right. That's a gray iron casting with some serious cracks. Believe me, that is not a coincidence. Those little flakes are the key to understanding, well, everything. This right here is the defining feature of gray iron. As that molten metal cools, the extra carbon doesn't form hard compounds like it does in other irons. Instead, it literally separates out, forming these interconnected flakes of soft graphite. And that's what gives a fractured surface its signature gray color. And it's how the material got its name. Now, I love this. One of the source documents had this fantastic analogy. It compares the graphite structure to potato chips glued together at a central point. It's just a perfect way to picture it, right? Imagine trying to pull apart a clump of potato chips. It takes almost no effort for the whole thing to just crumble. And that's basically what's happening inside the metal. So here's the big takeaway. From a purely mechanical standpoint, these sharp graphite flakes are acting like millions of tiny, pre-existing cracks. The moment you apply a pulling force, all that stress funnels right to the sharp tips of these flakes, and a crack can just rip right through the material with very little energy. And that is exactly why gray iron has low ductility and low toughness. Okay, so it seems like an open and shut case, right? These flakes are a fundamental flaw, a bug in the system. But that brings us right back to our original question. If it's so flawed, why is it still used everywhere? What if this supposed bug is actually a feature in disguise? And this is where the story takes a really cool turn. Let's re-examine these graphite flakes, but this time, not as a weakness, but as the source of gray iron's totally unique and incredibly valuable properties. Let's talk about its hidden superpowers, the ones no other material can replicate at the same price point. Okay, superpower number 1, vibration damping. You see, those same interconnected flakes that make it easy for cracks to spread also act like a built-in shock absorber. The soft graphite literally interrupts and soaks up vibrational energy, stopping it from traveling through the iron. This is exactly why it's used for machine beds and engine blocks. It makes them run smoother, quieter, and with way more accuracy.
And its second superpower? Incredible machinability. When you cut into gray iron, those graphite flakes cause the metal chips to break off nice and clean. Plus, the soft graphite itself acts as a solid lubricant for the cutting tools. All of this makes it exceptionally easy, fast, and cheap to machine into really complex shapes, which is a massive manufacturing advantage that saves a ton of time and money.
But here's the thing. These amazing properties aren't just some happy accident. No way. They are the result of precise, deliberate metallurgical control. Modern foundries don't just pour gray iron, they engineer it. right down to the microscopic level. This shows it perfectly. That flake structure isn't just random chaos. Metallurgists actually classify graphite flakes according to international standards, like these ASTM types you see here. And for the really critical jobs, they are laser-focused on getting a Type A structure that gives the best balance of properties. Seeing anything else is a big red flag that something went wrong in the process. And how do they get that control? Their very careful manipulation of the cooling rate and the precise chemical recipe of the molten iron. They even add tiny amounts of other elements called inoculants that help guide the graphite formation. This isn't old-school stuff. This is high-tech material science, designed to get a specific result every single time.
So what's the bottom line here? We really need to stop thinking of gray cast iron as outdated and start seeing it for what it truly is, a highly optimized engineering solution.
This table just sums it up perfectly. Look, gray iron isn't trying to be steel. It's making a brilliant strategic trade-off. It says, okay, I'll give up some tensile strength and ductility, the stuff where steel really shines, and in return, I'm going to give you world-class performance in vibration damping and machinability, all at a fraction of the cost. It's not a compromise, it's a choice. So let's just be crystal clear. Gray cast iron isn't weak. It is perfectly optimized for a very specific set of jobs. Its incredible value lies in this unique cocktail of properties that, frankly, no other material can match. It's the industrial baseline, because for so many applications, it is still, without a doubt, the best tool for the job. And that really leaves us with a final question to chew on. Gray cast iron shows us that even the most common materials can have a complex, fascinating story. It kind of makes you wonder, what other simple materials are out there, just hiding extraordinary science in plain sight? What about the concrete under our feet or the glass in our windows? What secrets are they holding?